So we're looking at applications. We already looked at area under a curve, area between curves. We're looking at kinematics, and then we have one more application, and that is the revolving an area around the x-axis to make a volume. So we're down to our last 4 days of content, really, and then we're going to review next Thursday, have our test on Monday, and we'll be done. Okay, so just a reminder here, though, how this works. Remember, our kinematics dealt with a displacement function. It was a horizontal or vertical movement back and forth, okay, over time. And we took the derivative to find the velocity. We took the derivative of velocity to find the acceleration, okay, or the second derivative of displacement gives us acceleration, okay. Now, if we know acceleration, we can now move backwards since we know how to integrate and figure out velocity. Understand here, though, we would need some information because remember we have that constant of integration. So often we'll need like maybe an initial velocity or something like that, or some kind of point to plug in so we could figure out what the constant is. But then we could do it again with velocity getting to displacement. This is the one that is most commonly used with IBSL. We will look at an example that goes from acceleration all the way to displacement, okay? But I will say the majority of the cases that you're going to see are simply going from velocity to displacement, okay? Now, let's look at one where we aren't actually integrating, but just to get our minds back in the swing of thinking about kinematics, and also relating this to area, okay? We have here a car is traveling along a straight road with a velocity time function illustrated, okay? So this function here we could call v of t. All right, now we don't have an expression for this. We'd have to make some kind of a piecewise function with a bunch of lines. But we have this function v of t. And I want you to think about part A here. What's the significance of the graph when it's above the t-axis or below the t-axis? If this represents our velocity. Okay? We can see where the velocity is increasing and decreasing. Speeding up or slowing down, true. Evan, you started to say something. Could you expand on that a little?
Maybe the car is going forward, it's going backward.
Okay, and that specifically explains what's happening when it's above the axis and below the axis. We can make these other observations about speeding up and slowing down, but here, between 0 and 0.3, we're moving forward, okay? So, and then moving forward, okay, or the positive direction, okay? And when it's below the t-axis, we're moving backwards, or the opposite direction. We may not actually be driving backwards, but we're moving backward. Okay? Or moving in the negative direction. Okay? So can someone describe our trip here? If this was us driving along, can we describe what's going on in the trip?
So we're just starting off. We gotta get that speed up. Right?
Okay.
I mean, we can make a little right turn or something, maybe. Or we get like a traffic light or
Cruise control.
what is the
Well, what?
Like constant.
Hang on. What is this?
That's constant.
This is constant. So what'd you say?
Cruise control.
Yeah, it's like we put it on cruise for.
It's like when you're on Alligator Alley and you're not doing anything for like 3 hours.
Yeah. All right. So here we are speeding up. You're right. and then we're cruising along. We're not standing still here. Our velocity is constant. Okay? So now what happens? We're slowing down.
Crosses the street.
Okay? Something's crossing the street, or we're at a red light, or something. Okay.
And the only person
Drove a
cut
little
you
bit
off.
too far.
Okay. So yeah, maybe we passed a parking space, or there's a tree in the road, we have to turn around, and that turning around here is what's happening right here. We just changed direction. Okay? And now we're cruising again, 20 kilometers an hour, back the direction we came, and then we slow down and come to a stop. Okay, so you could create your own story for this thing, you know. Now these are tenths of an hour, so each of these is about 6 minutes. Alright, so we're gradually increasing speed for 6 minutes, then we're cruising for 6 minutes. Then we slow down and come to a stop, probably because we realized we made the wrong turn or something. And we're sitting there for 6 minutes doing nothing, trying to figure out where we're supposed to be. So now we turn around, we realize we passed it, we go back, and then we end up at the spot that we wanted to be at. Okay? So again, like you could make your own story for this whole thing. But that's kind of the understanding, and that's good that you guys are able to pick up on all of those different things that are going on, okay? Especially like here, we're not moving at all, and then we actually change direction, okay? That's important, okay? Here, the velocity was increasing here, now it's decreasing. So what could we say about our acceleration in this range here? It's positive. What about right here? What's acceleration equal? 0. And then now it's negative. Okay? So again, just trying to make those connections from like we did before when we looked at kinematics. But now let's look at the applications. Alright? B and C are asking similar yet different things. Okay? One is the total distance traveled. This is like what the odometer spun through as you're driving. Okay? C is the final displacement. How far away from the starting point did we end up? We don't care what happened in the middle. Where did we end up? That's displacement. Okay? So, let's think about this in terms of integrals for a second. For part B, total distance traveled, what would we do with integrals here? We would have to integrate the velocity function, good, with respect to t. From 0 to 0.7 over here?
Yeah, sorry.
Okay. What do you guys think about this?
Don't think about it anymore, 'cause we said that.
That'd be to find the displacement.
So you gotta say policy.
Wait, what,
Wouldn't
Vikash?
that be to find the displacement, not the total distance?
Why are you saying that that would be the displacement?
Because from 0.4 to 0.7 it'll be negative. So
Okay.
you'd have to split it up.
There we go, okay? This actually is C. Okay? This is our displacement because from 0.4 to 0.7 is negative. We were going the opposite direction, okay? This isn't like, this is like Ferris Bueller, okay? If you drive the car in reverse, it's not going to take miles off of the odometer, right? Okay? So, so here, this is going to give us a net distance or displacement, okay? So we integrate from 0 to 0.7, we're going to get where we ended up. In order to get part B, Vikash said we need to split this up, okay? So how would we do this? 0 to 0.3 of v of t dt.
And then you could do like 0.4 to 0.7, but then you multiply it by -1.
Okay, 0.4 to 0.7. Since we know this is negative, we can just, like Evan said, we could just put minus that, because minus the negative will make it positive. If you prefer to put plus and then do absolute value, you could do that as well. However you choose to make it positive is up to you. Alright? So we have v of t dt here.
So if it's below the x-axis, then we're gonna put the negative, right?
Yes.
If it will be like 2 ups, we'll put a plus, right? To define all the total distance.
Yes. Yeah. Okay, so let's actually find these areas. Okay, these are trapezoids, so here's a little geometry review for us. What's the area of a trapezoid? Or a trapezium if you're looking on the IB formula booklet. They call it a trapezium. It's a British thing. Alright? And probably Canadian too. But trapezoid, how do we find the area?
Is it like number of sides
It's like
minus
the
two?
triangle and the square combined. I think.
Yeah.
Wait, what?
I think it's the triangle and the square combined. So like 1/2, probably, possibly, probably not.
Maybe.
You could break it into triangles and a rectangle if you wanted, okay, but there is a formula here. Remember, it's the average of the bases times the height. 1/2 b1 plus b2 times h. Does that ring a bell? Okay. Alright, well, let's do it, okay? Our base here is 3. The base up here is 1, so the average of those is 2. The height is 3 units. Okay, so our area up here will be 6. Okay? Now, down here, the base is 3, the height is 1. So again, the average of those is 2. The height only is 1. Okay? So the area would be 2, but since it's below, we'll say that that is a -2. Okay, so here, we're not actually doing integrals, but I wanted you to get the hang of expressing them as integrals here.
Wouldn't it be 12?
Do
For the
we,
first one, or no?
Hang on one second, I'm sorry.
what do we need to find the area?
The area, remember, for a trapezoid, it's base 1 plus base 2 divided by 2 times the height. So in the case of the first one, the bottom is 3, the top is 1 over 2 times the height is 3. So 4 over 2 is 2, 2 times 3 is 6.
But isn't the height like 60 or something? Velocity 60.
Oh, okay, yeah. I see what you mean.
Oh wait, yeah, sorry.
And it's like 0.1, 0.3.
You know what, yeah, I'm totally ignoring the scale of the x and y axis here. Yeah, let's redo that. Okay, so the base is actually a 0.3 and 0.1. 0.3 plus 0.1 over 2. And yeah, the height would be 60. Thank you. Alright? So our average of the bases is a 0.2 times 60. So that would be 12. Thank you. 12. Alright? So that area is 12. Over here, this is 0.3 plus 0.1 over 2 times 20. Okay? If you wanted to use -20, it would even give you the negative in there too. So we got a 0.2 times 20, which would be the -4. Okay? So, in this situation, we drove for 12 kilometers, stopped for 6 minutes, turned around and drove 4 kilometers back the way we came. Yes?
Wouldn't B and C be switched, like those equations? Because for displacement, it's how far away from the starting point that your end point is, right?
Yes.
So distance is how much you traveled in total, like how many miles or whatever your car went. But displacement is only how far away you are from the first thing.
Yeah.
So wouldn't,
So the integral from here all the way to here will keep this negative. So you have a 12 minus 4, you have 8 kilometers. Okay? Here, you have a 12 minus a negative 4, which is 16 kilometers. We drove a total of 16 kilometers. We ended up 8 kilometers away from where we started. Okay? Alright, that makes sense so far? Okay. Now let's see this kind of in action, alright? When we are trying to find total distance traveled,
Sorry, did we do the C? Did we plug in numbers for this?
yeah.
Oh.
Yeah, we
Did
found
put
total
12 minus
distance.
4?
12 minus negative 4 is 16.
That's for B.
That's for B. C was 12 plus a negative 4, which was 8. That was the 8. Okay. So here, when we are finding total distance, you have to find those changes of direction. That's where the sign diagram can be helpful. Okay? With our velocity graph on the last one, starting at 0 to 0.3, our velocity was positive, and then from 0.3 to 0.4, it was 0, and then from 0.4 down to 0.7, it was negative. Okay? So, while we don't have a critical value, we actually had a kind of a critical time period. Alright? But this shows us the intervals where our velocity is positive and where it's negative. So we need to integrate from 0 to 0.3 and then from 0.4 to 0.7. We could have done 0.3 to 0.7 and it still would have given us the same thing. Alright, but 0.4 to 0.7 in that case. With a continuous function like we'll be using most of the time, this will be the same value. Ours it wasn't because we had the little trapezoid drawing and stuff. Okay? Let's look at an example of this in action. We have a typical kinematics problem here where we're given a particle moving back and forth. It's starting at the origin and it's moving to the right at 5 centimeters per second. It accelerates with time according to the function a of t equals 4 minus 2t centimeters per second squared. Okay, and this we could do without a calculator, so we will do it without a calculator. Okay, so let's find the velocity function of the particle. How would I do that? Integrate. Integrate the acceleration to get your velocity. So the integral of 4 minus 2t dt is going to equal what?
4t minus t squared.
4t minus t squared, good. Plus c, alright? Now, how do we figure out what c is?
Plug in the centimeters.
Okay, they told us, pay attention to those beginning things that they tell you. A particle is initially, that means our time equals 0. Okay, so when t equals 0, v equals 5. Okay, or you could even say that v of 0 equals 5. That's how we're gonna figure out C in this case. So what does C have to equal here?
5.
It has to equal 5. Because if I plug in a 0 for T, I get 0 minus 0 plus C. That has to equal 5. So now I know V of T is 4T minus T squared plus 5. Okay? Now, they've asked us to sketch the graph from 0 to 6. This is something I really want to emphasize here because this is where you can lose some really easy marks. Okay? Anytime you are asked to sketch something and they give you a domain like this, make sure you only sketch the domain they give you. They will take off marks if you put arrows like it's going to continue. Alright? Also, you need to label the endpoints of the interval. Okay? When they ask you to sketch, they want the endpoints and any other significant points on the graph. So let's look at what that would look like here.
Sorry. We have 2t. Is it supposed to be 2t squared over 2?
2t squared over 2. Yeah. Okay. So we have this parabola. Okay, here's our parabola. Our velocity with respect to time. Okay. So as I'm sketching this, you know, I've got to go from 0 to 1, 2, 3, 4, 5, 6. Okay? Since it's a parabola, some significant points would be the zeros and also the vertex. Okay? Also, we already know that it hits at 0, 5. Okay? Another thing that I want to figure out is the end point. The end point is at 6, so if I plug in 6, I have 24 minus 36 is negative 12, plus 5 is a negative 7. So I have my other end point here at 6, negative 7. I'm not going to draw any of the parabola beyond that. Okay? So, let's find our zeros next. Okay? Obviously, between our y-intercept and our other endpoint, we've got to cross the x-axis. So, we're going to have a 0 here. Alright, so let's do this. We have a negative t squared plus 4t minus 5 equals 0. I'm going to get rid of a negative here. T squared minus 4t plus 5. Just multiply everything by a negative 1. And then this will factor. Okay? Oh wait, that was originally plus 5, so now it's negative 5. Yes?
So what are we trying to find by doing this?
Well, the first thing they ask us to do here is to sketch the graph of the velocity.
Yeah.
So that's what we're going to do. And then once we can see the graph, we'll be able to see the displacement and total distance. And really it's for the total distance. We need to find if there's any of the any of the motion that's going backwards. Okay, because for total distance we need to take the absolute value or the opposite of that. Okay. So we continue factoring here. We have a t minus 5 and a t plus 1. Okay. So I know that this is going to hit the x-axis at 5. If I had the whole parabola, it would also hit at negative 1. And if you wanted to like give yourself kind of a dotted line or a dotted part of that parabola to help you see it, you could. Okay, just make sure it's clear that your solution is just the part from 0 to 6. Okay. The other key feature here that we could find is the vertex. Now, where is the vertex going to be? What's t for the vertex?
5?
No, that's a 0.
I'm confused. Why don't we just plug in t equals 0? Well, we already have 0, but like 1, 2, 3, 4, 5, and 6.
If you want to do that, you can.
Okay.
Okay? You don't have to find all of those.
Okay.
So we've got our two zeros. Where is the vertex in relation to our zeros? We know this.
In between.
Halfway in between, okay? So 5 plus -1 is 4. Half of that's 2. So we know our vertex is going to be 2 something. So we plug in the 2 to the our velocity, and we get 8 minus 4 plus 5. So that's 9.
How did you get 2?
We averaged our zeros. The vertex on a parabola will always be at the average of the zeros. So here we have this point 2, 9. Okay? And now we can actually sketch our parabola. Okay? So we've got that. It's going to come down here, hit 5, and hit this endpoint. Okay? So this is a model of the velocity of this particle. Okay? So now I can see for part B, number 1, I'm just doing the integral from 0 to 6 of 4t minus t squared plus 5 dt. I don't care what's positive, what's negative. I just want displacement.
Wait,
How
sorry, quick question. Did you plug in 2 into the original equation?
into v of t.
Okay.
We plug in 2
The integral.
into here
Okay.
because that's the function we're trying to graph. Okay? If I'm trying to do part 2 down here though, total distance, I got to split it up. Now how am I going to split it up here?
From 0 to 5 and then from 5 to 6.
Yes, look at that change in direction. The change in direction happens when our velocity hits 0, right? So that right there is the change in direction. So we're going to integrate from 0 to 5, and then we're going to subtract the integral from 5 to 6. Okay? And again, we're integrating that velocity function. All right, so now we're ready to take the integral of these. The integral of 4t is 4t squared over 2, so that's 2t squared minus t cubed over 3 plus 5t. We're going to evaluate that from 0 to 6. When I plug in 0, it's going to equal 0. All right, so I know it's going to be something minus 0. When I plug in a 6, I have 2 times 36, which is 72, minus 6 cubed over 3. That's going to be a 36 times 2, which is a 72.
Wait, when,
And then plus 30. So this whole thing here equals 30. All right, and in our problem here, we're dealing with centimeters. So this is 30 centimeters. Our final displacement was 30 centimeters on the positive side of the origin. Okay. On the bottom here, we're finding total distance traveled. So we've split this up. We were going in the positive direction from 0 to 5. Then we were going in the negative direction from 5 to 6. So that's why we're subtracting that. Or we could say plus the absolute value, either way. And we'll be able to get this. So we already know the integral is 2t squared plus t cubed over 3 plus 5t. We're going to integrate that from 0 to 5. And then we're going to subtract the 2t squared
It's minus.
minus yeah, thanks, minus t cubed over 3 plus 5t from 5 to 6. Okay? So if we plug in a 5, we get 50 minus 125 over 3 plus 25 minus 0. Okay? Then minus, I'm going to put some parentheses here. If I plug in a 6, I already know what it equals when I get 6, right? Because I just did that up on the previous step. So I know that's 30. And I already know what we get for 5 too, because we just did that over here. So it's going to be minus that 50 minus 125 over 3 plus 25. Alright, so look for those cases where you don't have to do the same work twice. That'll save you some time there. Alright, so now it's just putting everything together here. We've got some negatives we got to be careful with. So we've got, let's see, 75 minus, it's going to be 41 2/3. Minus parentheses 30 minus 75 plus 4 2/3. I'm distributing that negative. Now I've got to distribute the other negative. Okay. So we have 75 minus 30 plus 75. That's going to be 180. Minus, that's going to be 46 1/3. So now I actually put the fraction with the integers, and we get 133 2/3. 133 2/3. That would be our total distance that our particle traveled. Okay? So, any questions here? Does this make sense?